Swayam Prabha. Digital India. Educated India.
So next we will consider multiphase flows where more than two phases are involved. So for example, we have solid and gaseous particles in liquid flow. So basically there are three phases present. So an example here is aeration in slurry flows, such as aerated sludge reactors for wastewater treatment. So in this case, what happens is that they introduce air or oxygen into the wastewater. Basically, the idea is that it enhances the microbial activity and keeps the biomass suspended in water. So this is a way in which the water can be treated and clean water can be obtained. The other example is microaeration in chocolate industry. So here the objective is to modify the texture and flavor of the chocolate. So here the air is introduced into this chocolate slurry such that bubbles are produced and we have air-filled pockets within the chocolates. The next category of this such kind of three-phase flows are solid plus liquid particles in gaseous flows such as scrubbers. So these are, as you can see here, these are basically used to clean dirty gas. So in this case, as you can see here, the gas enters from top and there is a series of nozzles which inject the liquid which can be water. So these water droplets trap the dust particles and the contaminated droplets are collected at the bottom while the clean air is extracted outside. So here we can have different configuration, for example, coaxial and counterflow configurations are possible. So a similar application is dust suppression units in various industries. So in this case also, as you can see here, series of nozzles are used to inject water sprays into an environment which is full of dust. So in a similar way, the water droplets capture the dust particles and it settles down. So basically here the main objective is to suppress the dust, while here the objective is to obtain the clean air. So you have seen various applications of multiphase flows in nature as well as in engineering applications, and it's really overwhelming and it highlights the importance of why we should study multiphase flows. But you might be wondering what exactly we are going to do in this course. Okay, so let me explain that through these examples. Okay, so before that, we can also consider some some other classifications of dispersed multiphase flows, and after that I will explain about the scope of this course. So we can also categorize or classify dispersed multiphase flows into based on particle loading, Reynolds number of the carrier phase, particle deformation, particle size distribution, presence of reaction, etc. So this one is, the first one is the most important classification. So here we can classify the dispersed multiphase flows into dilute, moderate and dense categories. So this is based on the particle volume loading ratio or particle to carrier phase mass or volume loading ratio basically. So we will see this in more detail later. So we can have dilute loading. So what is meant by dilute loading technically? This refers to a condition where the particles don't have any back effect on the carrier phase. So what is meant by back effect? This means that the particles, when they tend to modify the momentum and energy present in the carrier phase. So that is called back effect. So there is always an effect of the carrier phase on the particles. because the particles are transported due to the carrier phase. But if the loading is dilute, we won't have any back effect. Then we can have moderate loading where the back effect by particles are possible. So basically in this case the dispersed phase modifies the continuous phase properties. Then in case of dense loading, in addition to this back effect from the particles, we can have effects due to particle-particle interaction. This means that the loading is so high that the particles interact with each other. For example, they collide with each other, and this itself influences the carrier phase. Okay. So why this classification is important? Because the existing models or the numerical and experimental technique, they largely depend on the particle loading. So the techniques that you can use for dilute loading, okay, it may not be applicable for dense and moderate loading. Okay. Then we can have laminar and turbulent multiphase flows. So this is depending on the carrier phase, if it is laminar or turbulent. We can have situations where we have deforming particles and where we don't have particles which undergo deformation. For example, dust particles in air, they don't undergo deformation. While droplets in air, they may be deformed due to the aerodynamic forces. Similarly, we can have monodispersed and polydispersed particles in a flow. Monodispersed means the particle size is same. So if the particle size is same, most likely their behavior in the flow is also same. But if the particle size is distribution, and distribution is there, so particle size distribution exists and particle size range is wide, then they can show different behavior. So in addition to polydispersity, this can lead to polykinetic behavior, which means that the particle velocity will also be different. And then based on the presence of reaction, we can have non-reacting and reacting flow. So by reaction here, what do we mean? So here we can mean any type of reaction, either it is chemical reaction, for example, combustion. Combustion is a kind of chemical reaction. Okay. However, there are many different kind of chemical reactions which are possible. For instance, in case of urea water solution injection into the exhaust duct, let's say in a diesel engine, the urea undergoes a thermolysis and hydrolysis process through some reaction mechanisms, and ammonia is generated. So reaction is present there and it is not combustion. And similarly, we can have biological reaction also. Okay. Okay. So now let's look at some examples. So recently I had been to a supermarket and this caught my attention. So I quickly took out my mobile and recorded this video because I thought it is quite relevant to this course. So you see here we have decorative items. Okay. So for a moment we need not think about any application, but the physics is interesting. So you see that you have a column here of water or any liquid, some transparent liquid, and there are some particles. The particles suddenly start to move upward, as well as they are undergoing a swirling motion. Okay, or you can say the liquid is actually swirling. So there is a rotor which is rotating the liquid, and because of which the particles are lifted up. And as long as we have the rotation of the liquid, we have the particles floating, and then they settle down as soon as the rotor stops. Now here you see it was just beside this one. This is quite interesting. So the same thing is happening here, but now you see. So what is happening here? So here they have some thermocol particles, I think, which are very light. So they are always they stay at the top. Okay, but they are dragged towards the center and also downwards. Why do you think this is happening? And what does this signify? Somehow there is a force here which is trying to pull the particles downward. So what can be that force? So what is the difference between this, the left one and the right one? Nothing. The right one, we have some flow tracers. What is meant by flow tracers? That the particles which somehow they track the flow. And possibly what is happening is that as we have this rotational motion imparted on the liquid, it creates a low pressure zone at the center, and that causes the particles, okay, to be dragged down, and you see a clear presence of a vortex core. A very nice, beautiful vortex core is present. So now, from the perspective of multiphase flows, okay, what do we want to understand here? First question, what is the size of the particle? What size of particle would be lifted off? Or put it the other way, what is the maximum size of particle which can be lifted up? Okay, and what is the height that it can reach? Okay, then if we can't see any cross-sectional particle distribution here, but you imagine you take a cross cut here, then how the particles will be distributed in a cross-sectional plane? Okay, so how do we answer these questions? So to answer these questions, what we need is, you need to know the carrier phase behavior first. Okay, so which means that somehow we need to make an estimation of the fluid velocity. So if the rotational speed is given, okay, then can we estimate the fluid velocity and calculate the pressure drop at the center also. So once we have the fluid behavior with us, then that can help us to predict the particle size and the particle size which can be lifted up, and once it is lifted up, what is its trajectory and how far up it can go. Okay, so now I will give you an example of practical application. Let's say you have a startup, okay, and you are the CEO of that startup. This startup is to provide engineering solutions, okay, for a wide variety of multiphase flow problems. So a customer approaches you and tells you about the requirement. So they want to introduce some kind of new powder into the market. Let's say almond milk powder, something new which is not common. So they come and tells you that, can you design, develop and fabricate and install the spray dryer units for us to produce this powder. Okay, so what are the requirements from their side? So they have to give some technical requirement, right? So let's say they say that they need powder 100 kg per day. Okay, and they also mentions about the characteristics of the powder. say size distribution. Which means, let's say they tell you that, okay, from 50, the powder size should be about 50 micron to 200 micron, or say 500 micron. So you have to produce powders in this range. And maybe they tell you that, okay, this should be the shape of the powder, and this should be the texture, this should be the color, okay, etc. This is the input that you have. So now how will you proceed in the designing the spray dryer? So first you assume that, okay, now let's say I have the spray dryer unit and I will have 10 hours of operation. So this means that the powder production rate should be 10 kg per hour. Okay. So now if the powder production is 10 kg per hour, then you need to have a slurry, right? So you basically, in a spray dryer, what you have is, you have a spray chamber in which there is an injector. Okay. So the injector injects the slurry. Which slurry? Maybe they will tell you also. So you have to prepare some slurry. Let's say you milk this almond particles in milk. So that becomes a slurry. So let's say they provide that. So now you have this injector and in this chamber, and around that you have hot air flow. So this is a basic configuration of a spray dryer. Okay, you have some sections like this to collect powder. Okay. Okay, so once you have here the air carrying the particles, you need to direct it to some kind of separator, let's say cyclone separator, as we have already discussed. So that's a different thing. But here you have this. Okay. So now, what is the first step? You have to select some injector which can inject the slurry. Okay, so let's say you have selected. Let's say you have selected air assist injector. This is some kind of atomizer at this moment, you can think of like this, which will basically break this slurry to small slurry droplets. And also you know its size. The droplet size distribution you know, or the manufacturer for this injector will tell you that, okay, if you operate it with this operating condition, you will get particles in this size range. Fine. So then you have also the liquid flow rate, which is obtained from here. So you know that you have to produce 10 kg per hour powder. So this means that possibly you will have to use, let's say, 20 kg per hour of liquid, because the liquid contains the particle as well as the water. The water has to evaporate. Okay. So you know the flow rate of the liquid. Then you need to decide the flow rate of air also. Around this you have air. You need to decide the flow rate of air. You need to decide the the temperature of air. Okay. So now, how do you decide these parameters? And also importantly, you need to know the dimension of the spray dryer. So the basic dimensions are the diameter of the chamber and the length of the chamber. Okay. So the question is, how do you get how do you decide these parameters? So one way is that you say that, okay, I will start with some value. Let's say I will take diameter of 1 meter, okay, a length of, let's say, 2 meters, and I will have airflow at, let's say, 80 degree. Okay, like this you start. Okay. Now what is the problem with this approach? So if you randomly start, even if you look back to literature and see, okay, how are the designs, and you try to adopt, there is a possibility that you may go wrong because this is a new particles that you are going to produce. It may not work. Okay. So now what is the problem if it doesn't work? You can make another one, right? Yes, but it is obviously not cost effective. You cannot arbitrarily go on making one after other dry units and go on testing it. Okay, so then because let's say you have a postgraduate degree and you know that, okay, why you have a postgraduate degree, let's say in fluid thermal science, then you can immediately say that, okay, why not numerically simulate it? First of all, let's simulate this and see the performance, and then we will manufacture. Okay, so you decide to simulate. But even for your simulation, you need these basic parameters, right? Without this, how will you start your simulation? Okay, and in this case also, it may not be cost effective if you randomly start without any previous calculation. Then what you can do, you can try to do some basic analysis. Okay, so let's say you have a duct like this, a simple duct, okay, where you have air which is uniform. Okay, air is flowing with uniform velocity. Now let's say you inject one particle, one slurry droplet here. Okay, so how long it will take for the slurry to evaporate the water content? Can you calculate? That is the question. Okay, so for that purpose, you will write the transport equations for the particle. Okay, carrier phase or here in case of the airflow, you don't have to, because the airflow velocity is uniform and one particle is not going to modify your airflow temperature, velocity, etc. Okay, so then from that you can estimate, okay, this is the distance that I will need, okay, till the time the water evaporates. Okay, so for that you need to know a model for the droplet evaporation. What is the rate at which droplet evaporates? How will you know? You rely on a model. And after the water dries up, then whatever content remains, that may not be a solid content. It may also be sticky content that you have because the temperature is high. So you need more time for this to further dry up and become particles. So using this theoretical calculation, you can calculate, okay, my length, you can estimate some length. Okay, now when you have an injector, okay, so you cannot assume that the droplets would always be axial. Okay, so they may have some radial velocity also when you inject it. So it is possible that a droplet which is injected here, it comes and hits the wall here and it sticks to the wall. So that is where you need to know how far, means how far it can travel before it evaporates. That you need to decide, and that also you can calculate. For example, here instead of having a velocity in the same direction as the airflow, if I give it some velocity, then can you calculate how long it will take for the particles to come and hit here? And then, so this can help us to estimate what should be the diameter of the dry unit. Okay, so once you do these basic or first-hand calculations, you can set up. So first you have theoretical calculation. So this basically gives you first-hand estimate of the input parameters. And also in this theoretical model, you can vary, let's say, air temperature, particle size, initial particle temperature, lot of modification, lot of input you can give and see its effect. And then with that knowledge, you can do a numerical simulation. Okay, and you do a parametric study. And once you perform the simulation, then you can make a, let's say, a prototype or say pilot scale and do the testing, the actual testing. For example, you can collect the particles and see the particle size, particle characteristics, particle texture, color, you can see that. But unfortunately, what happens is that this kind of flow that I have shown here is practically not possible always. Why? Because the simulations themselves require several models. Okay, and you need to validate the results from the simulations. Otherwise, how do you know they are right or wrong? So you need input from experiment. Okay, so and also the models, to develop models, you need input from experiment as well as simulations which are targeted towards understanding the physics of the problem, where you consider a very fundamental problem. Okay, so these are high-end simulations. For example, you do direct numerical simulation, but with that it is not possible to simulate this entire rig. So you can consider a fundamental aspect and do a detailed simulation that can also help the models. So you see that they are all closely coupled to each other. Okay, and so the main objective of this course is to give you an overview of the multiphase flows and to introduce you to this analytical calculation of the multiphase flows. Okay, of course, in simple scenarios. Okay, and then also to give you an overview of this simulation and experimental techniques which are existing in multiphase flow studies. So we understand that for study of multiphase flows, there is a need to develop accurate models. Okay, and so that we can predict detailed behavior of the flows and the flow phenomena. But in order to validate the existing theoretical models and also the simulations, and also to gain insight into the complex interface coupling mechanism, detailed measurements are also very important. So this present course intends to give a fundamental perspective on dispersed multiphase flows while demonstrating the application of simple models to make useful predictions for practical cases. Okay, and we will, as I said, we will have a discussion on numerical and experimental methods, and in between we will have a dedicated section on the role of turbulence on particles. So till now we didn't discuss about the role of turbulence, or at least I didn't highlight, but there will be one separate section where we'll discuss this, and accordingly. So the main objective, as I said, of this course is to provide a basic understanding on dispersed multiphase flows and to demonstrate the challenges encountered in its prediction and measurement. So the course has broadly the course has 5 modules. The first one is fundamentals and the transport equations for the dispersed phase and carrier phase. The second one is modeling transport of particles, where the carrier phase is prescribed. So we don't have to bother about the carrier phase, we only model and predict the particle phase behavior. And then particle turbulence interaction, then an overview of the numerical modeling and experimental methods. So the outcome of this course is that it will enable you to have the analytical ability so that you can formulate basic models for particle dynamics in any kind of multiphase flow. So that is the objective. That is the, I would say, the most important objective here. So the multiphase problem, it can be, whatever it can be, or whatever range of multiphase flows you encounter, whether it is respiratory droplet transport during sneezing or coughing action, or transport of urea droplets, or transport of particles in a spray dryer. Okay, whatever is the multiphase flow, you should be able to do a basic analytical calculation, okay, to predict the particle behavior. And then an overview of the existing numerical and experimental techniques are also will also be given. Okay, so that is also very important, so that you can decide which technique to apply depending on the problem that you are considering. And this is the syllabus of the course. So as I said, there are 5 modules. So each module is shown in a different color. So here, this part we have already discussed. I have already given you an introduction on the multiphase flows. Next, we will consider some properties, key properties of the multiphase flows, and then this is the theoretical modeling part. So here we will consider the mass, momentum and energy equations for the particle phase and for the carrier phase, and then we will consider one-dimensional transport and simple models for practical applications. And then this is the particle turbulence interaction, where first I will give a brief overview of turbulence itself, and then effect of turbulence on particles. And in particular, we'll spend some time on understanding turbulent dispersion in sprays, or where you have liquid particles in a gaseous medium. And then I will discuss the numerical modeling, the key approaches which exist in understanding the multiphase flows, and then experimental methods in multiphase flows, where we will focus on measuring not only the dispersed phase, but also how to measure the dispersed phase and the carrier phase simultaneously at the same time. And these are the references. So the first one is Multiphase Flows with Droplets and Particles by Crow and Sommerfeld. It's a very good book, so we'll closely follow this. But there are other good books also. So Fluid Dynamics of Particles, Droplet and Bubbles by Eric Loth, and Multiphase Flow Handbook, then Fundamentals of Multiphase Flow by Christopher Brain. Okay, so all these books are very good on the basics of the properties of dispersed multiphase flows. But before we discuss this, it is very important to discuss the continuum hypothesis. So when you study a fluid mechanics or heat transfer course, first thing that you learn is that we treat the fluid medium as continuous. So what is meant by that? Is it actually continuous? Let's say you have air flow, let's say flow of air over a flat plate. Okay, so there, for example, our interest is on the how the boundary layer development, the drag on the plate. Okay, so for that we treat the fluid as continuous, but we know that in this case the molecules are far apart. So why on what basis we treat this as continuous? Any answer?
Macroscopic approach.
So the assumption of the continuum, the continuum assumption or hypothesis is essential, first of all, to define all the properties. For example, let's say pressure, let's say density. So now let's consider you have some gas here in a container. Okay. So you have molecules here. And now what is pressure? What is pressure exerted by the gas? How do we define it? The force exerted by the gas per unit area is pressure. So now if I consider some area here, let's say, okay. So now if I ask what is pressure? Again, this is the momentum transferred by the particles when they hit the, or by the molecules when they hit the wall of the chamber. Okay. So now you consider any one time instant, okay, and see how many molecules are colliding with the wall. Let's say you make a note of that. Then you consider another time instant at the same location. Do you expect the number of molecules, gas molecules, which are colliding the wall to be same at different time instants? The answer is no. But do you expect then the force to be different? Because the force, you have the force because the particles are hitting the wall. And if the number of particles which are hitting the walls is different, then the force also should be different. So force should be a function of time at a particular location. Okay. Then I consider another location, say here. Okay. Now at the same time, I wouldn't expect the same number of molecules to collide with the wall at two different locations. So this means that pressure should be a function of space and time both. Okay. But now you bring a pressure gauge and you install it here. And you bring another pressure gauge and you install it here. What will you see? Pressure is same and the dial does not change with time. So this means that pressure is not a function of space or time. Why? This is because the continuum assumption gets automatically validated here. Why? Because the physical dimensions that you are considering, the time scales that you are considering are much longer than the time scale involved in the molecular motion of the molecules. Okay. So that is the reason why the pressure does not vary with space or time. Okay. So the same goes with, for example, definition of density. So what is density? Mass of a material per unit volume. So again, if you consider some region in a fluid, okay, and you have and you count how many molecules you have, okay, and then you know the mass. Okay, let's consider nitrogen. Okay, so you have nitrogen flow and you have considered some region where you know the volume, you calculate the mass and you calculate the density. Now I change the volume. Okay, should I get the same answer? You can imagine you go on zooming into the flow. Okay, so such that you are in a region, in a very small region. Okay, here you can see molecules some way. Okay, and now you do this. So at any instant of time, you see how many molecules you have within this. Okay, you calculate density. Okay, and then the next time instant, you see how many molecules are there. Should they be same? No. Why? What is the difference? In earlier case, it was same, but now it is not same because you are considering a dimension which scales with the mean free path of the molecules. So what is meant by mean free path? In simple words, mean free path is the average distance that a molecule travels before colliding with another molecule. So your dimension now scales with the mean free path. So that is the reason why at that scale it is not continuous. But for all practical purposes, for all engineering applications, we can safely assume that these dimensions, our dimensions, are much longer than the mean free path. That is why the fluid is continuous. So basically here, these the control volume here, we say that it approaches zero, but it should not be zero. There is some critical volume, okay, below which this definition won't work. Okay, but this volume is zero for all practical purposes. Okay, but now interesting thing comes up, that is, does continuum approximation for the carrier phase? So please note that till now we are only talking about the carrier phase, this continuum assumption that you have studied in the fluid mechanics. So that is now valid for carrier phase. But does this ensure that the dispersed phase can be analyzed accordingly? Now, what does that mean? So now let's say you have, let's say you have a flow of air and I release one particle in the air. Okay. So here you have airflow. Okay. Let's say you are considering airflow in a channel where the dimensions are obviously much larger than the mean free path. But now you have one particle here. Okay. So we are interested in the transport of the particle. So if I release one particle, how far it will travel before it settles down due to gravity, let's say. So for that, you need to calculate what is the force on the particle. And what is that force? Drag force. Okay. Now, from a microscopic point of view, what is drag force? It is the interaction, it is due to the interaction between the carrier phase and this particle, right? So you have, now imagine you just zoom in and these are the molecules. So these molecules come and bombard on the particle and that is what is causing the drag force. Okay, so the continuous phase is, or the carrier phase is continuous according to our continuum hypothesis. Okay, but now you imagine the same question arises. Should the drag force be a function of time? Because the number of molecules which are bombarding on the particle is different, is changing with time. Are you getting it? So basically what I am trying to convey here is that the continuum assumption for the carrier phase does not guarantee that continuum assumption is valid for the dispersed phase analysis also. So how do we deal with this? So that is why we define something called a Knudsen number. Okay. So this number is defined as the ratio of the mean free path to the particle size. Okay. So we consider that the continuum assumption is valid in dispersed multiphase flow if the Knudsen number is less than 0.003. So this means that the mean free path, okay, is much less than the particle size. Okay. So in this example that I gave, that I released one particle in the flow, the particle size must be much larger than the mean free path. Then we can assume that yes, we have continuum hypothesis valid here also. Okay. But obviously now it depends on the particle size that you are considering. So if you have, let's say, a particle, for example, you have So let's say that you have flow of nitrogen. So if we assume that air, nitrogen basically represents air, then the mean free path for nitrogen, okay, is 10 to the power of -7 meter, and for a diameter of 10 micron particle. Now let's say you have, let's say solid particle, let's say coal particle, okay, which has a size of 10 micron. Then what is the Knudsen number? So 10 micron size is practically in many applications we encounter. So the Knudsen number is 0.01, around that. Okay. So is this satisfying this criteria? Okay. So the answer is no. So is the continuum assumption valid in this case? Most likely no. But should we do the conventional analysis that we are doing? What is meant by conventional analysis? So let's say you have this particle, okay, this particle is flowing in the flow. So if we assume spherical particle, then what is the drag force? If we invoke Stokes flow hypothesis, that is the Reynolds number of the particle is very low, which likely will be the case because the particle size is small, then we can say that the drag force is equal to 3 pi mu v d. That is what we learn from Stokes flow analysis, right? But the question is this valid? We can calculate the drag force, but how far this is valid? This is an open question even till now. Okay, so we'll stop here. In the next class, we'll discuss the key nomenclatures associated with dispersed multiphase flows. Thank you.